Hello and Assalamu alaikum students. In this lecture we are going to learn about waves. We will study types of waves, transverse and longitudinal waves, interference of waves, sound waves and Doppler effect. First let's look at the definition of waves. Wave is actually a disturbance that travels through a medium or in vacuum, means through a medium or a region without a medium from one place to another by the transfer of energy. So this disturbance is called as wave. There are three different types of waves, which are mechanical wave, electromagnetic waves and matter waves. Mechanical waves are those waves which can exist and propagate only within a material medium. The medium which is consisting of material such as water, air and rock. These are material mediums. While electromagnetic waves are the waves that require no material medium like vacuum. And the type of such waves are light waves, because light waves can travel through a medium, means travel through a region without any medium like space is vacuum. It does not carry a medium, it does not carry a material medium, but light can still pass through that and reach us on earth. So that is why light is a type of wave that does not require a medium to propagate from one place to another, and it is called as these waves are called, such waves are called as electromagnetic waves. And matter waves are those waves which are associated with matter. These waves are also called as de Broglie waves and are central part of quantum theory. These we are not going to study these waves here. So actually these are the waves which are associated with each particle of matter. Here is an example. This blue line is representing wave and this c is the velocity of the wave, and the arrow is indicating the direction of movement of wave. So wave is moving along x-axis, while these red spots, these are representing the particle of the medium, and they are oscillating up and down along this central axis, and this oscillation is perpendicular to the direction of wave propagation, right? So such a wave is called as transverse wave. Is longitudinal wave. So in contrast to transverse wave, longitudinal waves are the waves which involve oscillation of the medium particles along the direction or parallel to the direction of wave propagation. In transverse waves, the motion of the particle, medium particle, is perpendicular to the direction of wave propagation, but in longitudinal waves it is parallel to the direction of the wave propagation. So here is an example. The wave propagating through a spring is longitudinal wave. So you see that the wave is moving in this direction, while the particles of the spring are also oscillating parallel to this motion. Okay, and you know that the wave is defined as the disturbance that carries energy with it, right? So it is transporting energy from one place to another. That's why it is mentioned as energy transport, right? And particles are moving along the x-axis also, and the wave is also moving along x-axis. So the movement of the particles and the direction of wave propagation are parallel to each other, and such waves are called as mechanical waves are called as longitudinal waves. Here is another example of longitudinal waves. This is, you can consider this as an arrangement of atoms inside a solid material. So they are very close together. So when wave propagates through a solid medium, so this is how the wave or the energy propagates through it, transfers from one place to another. So these particles transfer energy to these, and they to the next one, these to the next, and so on. So this is also an example of longitudinal waves, because the particles, if you look carefully, these are only moving along this direction, okay, parallel to the direction of the propagation of the wave. Okay, now these oscillations, up and down oscillations, are referred to as sinusoidal wave, like this. So this one is the, if this is the particle, this let us consider this one is a particle, so it will move up and down, and the wave moves perpendicular to it. So this waveform that is generated as a result of the oscillation of these particles is called as sinusoidal wave. And sinusoidal wave has a crest and a trough. The crest is this one, the upper one, and the trough is the bottom one. And one crest plus one trough makes one wavelength. Okay, so the distance between two crests or two troughs, or from a crest until the trough ends, is one wavelength, right? And the distance of the maximum distance of the wave from the origin or from the zero axis upwards is the amplitude. This is called as amplitude. Here this ym, or maximum y amplitude, from here until here, this one, this it starts from here and ends here, right? So this one is the amplitude of the wave, okay, and the time during which one wavelength crosses one point is called as the time period. Okay, this is the time axis, horizontal, because the wave is moving along it, the time it takes to pass through one point, the time it takes for one crest and one trough to pass through a point is called as time period of that wave. Okay, and its equation is written like this: y, this y amplitude, because it is varying, right? So amplitude is the middle one, but it varies with time. Okay, x-axis is time, y-axis is the amplitude or intensity. So it varies with time, and it is represented like this: ym is the magnitude, or sorry, amplitude, this one, times sine of kx minus omega t. Okay, so what are these terms? This one is the displacement, vertical displacement, while this central part is the amplitude. Okay, ym is the amplitude, and then this one is the sinusoidal part, or the oscillating term, the one that is oscillating up and down. This one defines the shape of this wave, and then the central part is called as phase, where this k is the wave number, and it is calculated by 2 pi over lambda, and lambda is the wavelength, the length of one wave. And here x is the position, and omega is the angular frequency. It is calculated by 2 pi over t. Here capital T is the time period of one wave, and this one is time. Okay, means any time on this x-axis. So this one defines that at what time what will be the displacement of the particle from this x or time axis, horizontal axis. Okay, now what is the principle of superposition? It states that overlapping with algebraically, the overlapping waves means that when two waves cross through one point, they overlap with each other. When they are overlapping, they algebraically add to produce a resultant wave or the net wave. Means when two waves are crossing each other, they will definitely overlap with each other. So when they overlap, their amplitudes algebraically add. Means 4 plus 4 8, 2 plus 2 4, and 4 plus 2 6. It means if the amplitude of one wave is 4 and the other wave has an amplitude of 6, both will add up and they will give another wave that has amplitude equal to the sum of the both. Means if one wave has 4 amplitude and the other one has 6, then the net wave or the resultant wave will have an amplitude of 10. And second is, the overlapping waves do not in any way alter the travel of each other. So both waves will keep on traveling as they were. They were only superimposed with each other when they come in contact or they are crossing from one point, but they keep on traveling unaltered. So on the region where they are overlapping, they will produce a resultant wave, but they will, after that, they will separate from each other. So mathematically we can express like this, that this is the amplitude of the resultant wave with a prime on it. So this is the amplitude of one wave and this is the amplitude of second wave. So when they superimpose with each other, okay, or when they cross each other, then their amplitudes at a certain time t, they add up and give a resultant amplitude as a resultant wave or net wave. So here is a demonstration of that. Let us consider these two waves y1. This wave has amplitude y1 and this one has amplitude y2. So this one is moving rightwards, this one is moving leftwards. So when they come in contact with each other, they pass through this point. See, these two came closer. When they pass through the same point, they superimpose with each other and generate a resultant wave, a bigger wave. Its amplitude is equal to the amplitude of this wave and the amplitude of the second wave. Okay, this is the equation for this wave. And after, when they have passed, see, this small wave is going this way, this one is going the other way. So they keep on moving as they were before. They separate from each other. The blue one goes to the left side and y1 goes to the right side, then they continue their travel. So this one is the first sentence here, the first sentence of the statement, and second one is related to the second one. At first one, when they superimpose, their amplitudes algebraically add to give a resultant wave, and after that these both waves do not alter each other's travel. So they keep on traveling unaltered once they pass through them, once they have passed or crossed from that point. Okay, now the interference of waves. When the waves interfere with each other, what happens? Like the superposition. So the resultant waves depend on the extent to which the waves are in phase with each other, i.e. how much one waveform is shifted from the other waveform. Let's see one example. When both waves, this wave and this wave, when they are superimposing with each other, they come in contact or they cross from one point at the same time, and if they are in phase means that they are starting exactly at the same time and ending exactly at the same time. This is called being in phase. So these two waves are in phase with each other. Then the interference happens and the resultant wave is produced, like we saw before, and the resultant wave has an amplitude which is equal to the sum of these two amplitudes. Okay, so if this was 2 and this is also 2, this will be 4 and this will also be 4. If this is 2 and this is 6, this will be 8 and this will also be 8. Such interference is termed as constructive interference. Okay, and in the opposite to it if these waves are totally out of phase. Like in this case, these are totally out of phase. So this one has a crest and this one has a trough at the same position. Okay, so when the first wave has trough, the second wave has crest. So this is 180 degrees shift from each other. So they are out of phase by 180 degrees. So when such waves meet with each other and their amplitudes are also same, but these are in opposite direction, this is +2, then this is -2, this is +2 and this is -2. So when they add up together, they cancel each other. Destructive interference has occurred. There is no wave when they are crossing each other, so they destroy each other. This is called as destructive interference. But according to this principle of superposition, they should not alter each other's travel. They should continue traveling, right? But why? But when they do the destructive interference, they destroy each other, right? So how they can continue their travel? Actually, this destructive interference is only at the place where they are meeting. After that, they continue their travel as they were. Let's see here. So this is a constructive interference. Wave A is traveling in the towards right and wave B is traveling towards left. So this situation is before interference. They are approaching each other. So when they meet, the amplitude of the resultant wave becomes A plus B. When they meet each other, they generate a new wave. Okay, so this one is with a black one or dark blue. So this wave has an amplitude equal to the amplitude of wave A plus amplitude of wave B. So this is the during interference, and after this interference they keep on traveling as they were traveling before. They separate from each other and then continue their travel. This was after interference. Let's see it in action. So there are two waves approaching each other. When they approach, they make a big wave and then they separate from each other and continue their travel. Now let's see the destructive interference. This one, the wave A is approaching to is moving towards right and wave B is moving towards left. So as they approach each other and they cross each other at the same point here, they meet each other and their amplitudes add up. So its amplitude is positive, its amplitude is negative. They cancel each other and they produce this stationary wave. Still not the stationary wave. They produce nothing but a straight flat surface, a stationary surface. So this thing happens during the interference. So when the interference is open, once the interference is over, because A was moving in this direction, B was moving in this direction, when they continue travel a little further, they retain their shape back again and then keep on traveling as they were before interference. Okay, let's see that in action. When these two waves approaching each other out of phase, they meet, cancel each other and then continue traveling back again. Okay, now sound waves. Sound waves are actually mechanical waves, means these are the waves which require medium to travel from one place to another, and they are longitudinal waves, means that during their propagation the particle of the medium oscillate along or parallel to the direction of propagation of waves. So these are mechanical waves and their type is longitudinal, means they are mechanical waves and their subtype is longitudinal waves, because you saw previously there were two, longitudinal and transverse. So in transverse, the particles of the medium move vertical to the direction of propagation of waves, while in longitudinal they oscillate parallel to the propagation of the wave. Here this is the source S. Okay, this one is source S, and the sound waves are traveling in all directions around this source. You can consider this as a loudspeaker, and the waves are traveling around it. Okay, so it's facing upwards, or and then it is creating sound waves in all directions around it. So these pink ones or light purple ones, these are the wave fronts. Wave fronts are the parts of the wave in which are the parts of the medium at which all the waves are in phase, or you can consider them crests here. And these ones are the troughs, or in terms of longitudinal waves we call these regions compressions and these empty regions as rarefactions. So these are the wave fronts, and this one is ray actually indicates the direction of motion of the waves, of the longitudinal waves, and this one double-headed arrow around this green point indicates the direction of the oscillation of the particles. So particles are oscillating perpendicular to the parallel to the direction of the propagation of wave. Waves are propagating along ray, and this particle of the medium is oscillating parallel to that direction, and the particle of the medium here is also oscillating along or parallel to the ray, which is the direction of the propagation of wave. So the frequency, the frequency is how many waves pass through a certain point in 1 second, is the frequency. The sound waves have a wide range of frequencies, but only the audible range is 20 hertz to 20 kilohertz. We can hear sounds between this region only, and these waves are called as sound waves. Above it are called as ultrasonics, and below this frequency, below 20 hertz, are called as infrasonics, and above 20 kilohertz are called as ultrasonics. So this is not this one, this is 20 hertz. Okay, this is not 20 kilohertz, and this is also 20, this is 20 hertz to 20 kilohertz. And the speed of sound in air is 343 meters per second. Means when sound is produced in air, it can travel through it at a speed of 343 meters in 1 second. So this was the definition of the wave fronts here. So wave fronts and rays indicate the direction of the travel of the speed in the medium. You can see this is you can consider this as gas or air through which the sound waves are traveling. So sound waves, like you saw a spring, the spring has some compressions and rarefactions when the longitudinal wave passed through it, or you saw the atoms of the medium when they were transferring the wave from one place to another. Some parts get compressed and other parts becomes relaxed. So these compressions and this expansion or rarefactions can be related to crests and troughs of a sinusoidal wave, and the distance between two consecutive compressions is called as wavelength. So if we expand it, if we want to go deeper into it, we expand this small region and we highlight this small region around it, small part of the air around it. So it oscillates, so this distance we are calling it delta x, and this is the part that is oscillating like this. Okay, So in order to make the sound wave move from one place to another, so this one is the oscillating fluid element. This one oscillates like this. So Sm is the maximum displacement from this position. It goes from here and it goes towards here and then here. So it is traveling like this. Sorry, it is oscillating like this. So it goes from here its amplitude, its displacement is 0, and here it is maximum. This is the amplitude, and then it comes back here and then goes back. So it keeps on oscillating like this. Now we can write an expression for it. So this one is written in terms of cosine function. The previous one was written in as sine function. So the only difference between sine and cosine is that cosine, there is a phase difference of 90 degrees between sine and cosine. Cos starts from 90 degrees while sine starts from 0 degrees. So first, this displacement function, this one can be written like this: s, this distance s, is equal to sm. Sm is this one, the amplitude, like in the previous case it was ym, and cos of kx omega t. So all these terms are same: wave function, displacement, angular frequency 2 pi over t, and t is the time. This omega is equal to 2 pi over t, that capital T is the time period of the wave, and this one is any time on the time axis, any specific time at which we want to, this t is any specific time at which we want to measure this displacement from this equilibrium position. And the pressure, because it is compression and rarefaction, so pressure can be determined like this. It is very simple, just replace this with delta p, and this one with sine. Actually we can represent this with sine as well. Kx minus omega t, and the amplitude, this one delta pm, is expressed like this. The amplitude of the pressure means that where the pressure will be maximum. So delta pm is equal to nu rho omega sm. Sm is this amplitude, omega is angular frequency, v is the velocity, and rho is the density of the medium through which these sound waves are propagating. Okay, now the last one is Doppler's effect. Doppler's effect actually tells us about the shift in the frequency when the source or detector are when source and detector are in motion with relative or with respect to each other. You must have observed that when you move towards a source which is producing sound, you observe a change. You feel it louder, and when you move it away, you feel it, the sound intensity is decreasing or it's getting fainter, right? So Doppler's effect explains that when the motion of a detector can be your ear, or the source can be anything which is producing sound, is toward each other. When detector or source are moving towards each other, means the distance is decreasing between them. The sign on its speed must give an upward shift in the frequency. The frequency of the sound increases, means that the frequency will be increased, more waves will be compressed into a smaller distance. The motion of the detector or source is away from other. When the source and detector are moving away from each other, means the distance between the speaker or any source of sound is increasing, means you are moving away, or the source of sound is moving away from you. In any case, when the distance between the source and the detector is increasing, there is a downward shift in the frequency, means that the frequency of the sound wave appears to decrease. So in general it can be expressed with this formula, where f prime is the shift in frequency, f is the original frequency which is emitted by the sound, this v is the speed of sound in air, this v is the speed of the detector's movement, the detector is moving with certain velocity, this v is again the speed of sound in air, and vs is the speed of the source. Okay, so this plus minus, we have to use one of these signs depending on, we have to choose depending on the relative motion of the detector and the source, right? You will see how and which sign we can choose. First is the shift up, this is the ear or the detector, and this one is the source, and these circles are the wavefronts of the sound emitted by this source. So the source is stationary here, Vs or the velocity or the speed of sound, the speed of the source is 0, it is stationary, but the detector is moving, our ear is moving, the detector is moving towards the source, so it is moving towards the source, and in that case there must be an upward shift in the frequency. It should appear that as the frequency of the sound has increased. So detector is moving but the source is stable. Then our general formula, which is this one, can become like this, because the velocity of the source here is 0, it is not moving, so we will replace Vs with 0, and V is the speed of sound, it will stay like that, V here, but on the top we are choosing positive sign. Why? Because the detector is moving towards the source there, and the distance between the source and detector is decreasing, so when the distance decrease the frequency increases. That is why we have to put a sign, positive sign, between the speed of sound in air and the velocity or the speed of the detector. If they were moving away from each other, then we will use negative sign here. Okay, if the detector is moving away from the source, then we will use this formula, means if the ear was moving away in this direction, then we will use negative sign between these two. So in general we add both signs, but in the specific case when the detector is moving towards the source and source is stationary, we put Vs is equal to 0 and we use positive sign, and when the detector the source is still stationary but the detector is moving away from it, then we use negative sign between the speed of sound and Vd, or the speed of the detector. Here remember that this f is the original frequency of the sound that is emitted by the source, and the f prime is actually the resultant or the shifted frequency. This is how it can be represented. Now the ear or the detector is stationary here, Vd is 0, but the source is moving towards the detector. Again, the distance between the detector and the source is decreasing, therefore there must be a shift up, because the source is moving towards the detector. Then our general formula can be written like this, that for stationary source Vd will be equal to 0, means this part, this Vd will be equal to 0, so V divided by V minus Vs. Why is that so? That why we are using minus sign here? Just think about it for a while, then I will tell you the reason. Okay, so the reason is that when the distance between them is decreasing, there is an upshift, right? So in order to increase the value of a fraction, or you know that the denominator should decrease. Okay, since we have the values on the denominator here, the source and the speed of sound, so if we use plus sign, it will decrease the overall ratio, right? But we know that when they are moving close to each other, there should be an increase, right? So we have to use negative sign because there is an upshift. So if it had been on the numerator, then we will use plus sign as we did before, but source is on the denominator side. So in order to observe an increase in the fraction, we must decrease the value of denominator. So that can be done only by putting negative sign instead of positive here. Okay, so this was the case when the source was moving towards the ear or the detector. So what if the source is moving away from the detector? So when the source moves away from the detector, there must be a downshift, right? So the frequency should decrease when they're moving away. Then we will use positive sign here between the two, right? So here we are using V plus Vs, so it will decrease the overall value here, causing a downshift. Let's do an example now. In this example, bats navigate and search out prey by emitting and then detecting reflections of ultrasonic waves. You know, bats produce ultrasonic waves and navigate through with the help of the reflection of those ultrasonic waves. We cannot hear them because they are ultrasonics, and beyond our audible frequency range, means that higher than 20 kilohertz we cannot hear, but bats can use them to navigate. So when they strike or hit an obstacle or a wall or anything, they reflect back, and the bats process that information and can navigate using those reflected waves. So in this now when the bats are um, releasing some ultrasonic waves, they to search out prey, means any type of insects or something, that when they come into the range of their ultrasonic waves, they strike the prey and then reflect it back. So suppose bat emits ultrasonic waves at this frequency. So this is bat emission FBE. So the frequency of the sound waves frequency of the ultrasonic waves emitted by the bat. They are emitting at 82.52 kilohertz while flying with this velocity. This is the velocity of the bat, and you know this I unit vector, it represents the positive x-axis direction as it chases a moth. So moth is the prey, so bat is flying behind the moth, it is chasing that moth and navigating with the help of ultrasonic waves. Because they cannot see with their eyes, they have to rely on the ultrasonic waves which are reflecting back, like we see objects through the light which reflects from the walls and all the objects, right? So similarly, instead of light, the bats use ultrasonic waves. The difference is that the ultrasonic waves are produced by themselves, but we use sunlight or any other source of light that falls on something, then reflects and enter our eyes, while bats produce their own ultrasonic waves which hit something and reflect back, and their sensors observe it. Okay, the moth is flying with this velocity Vm 8.00 meters per second, also in the same direction. So means bat and the moth both are moving in the same direction but with different velocities. Bat is moving with 9 meters per second and moth is moving with 8 meters per second. What frequency? BD. So after reflection, this should be the one that is detected by the bat. This BE is the emitted by bat and BD means the one that is detected by the bat. Does the bat detect returning echo from the moth? Means that when the wave hits the moth and this ultrasonic wave and then comes back, what will be the frequency of that wave when the bat detects it? So the considering the speed of sound is 4.343 meters per second. So given data, this is the given data, that the frequency of ultrasonic waves emitted by the bat is this, velocity of the bat is this, velocity of the moth is this, and the frequency of the echo is the reflected wave. So frequency of the echo detected by the bat is the one that we have to find out. Now we will use Doppler's effect here. Take a moment and think which one will be the source and which one will be the detector. Okay, the first case, when the bat emits the ultrasonic waves, then this bat is the emitter or the source and it is going towards the moth, so moth is the detector before it reflects from there. Okay, so when the wave is ultrasonic waves are generated by the bat becomes the source and it goes and hit the moth and moth becomes the detector. And since the moth is moving away from the bat and bat is moving towards the moth, so we can write it like this. So just remember the formulas before. When the detector was moving away, we have to use negative sign, right? And when the detector is moving towards the source is moving towards the detector, then we have to use negative sign here, because this one is for the detector, this one is the velocity of the detector, and this one is velocity of the source. So when detector moves away, because moth is moving away from the bat but bat is moving towards the moth, right? So the detector is moving away from the source and source is moving towards the detector. So when the detector is moving away from the source, we use negative sign here. This is the velocity of the sound, this is the velocity or speed of the detector or moth. So when the detector moves away, we use negative sign between the two, and when the source is moving towards the detector, we use negative sign here. Okay, so this one is the frequency that is detected by the moth. Okay, and this is the original frequency, means the frequency that was generated by the bat. This one, the frequency of the ultrasound waves emitted by the bat. Now we put the values here and calculate the frequency which was detected by the moth. Now why we needed this frequency? We were actually asked to calculate the frequency of the echo detected by the bat. So echo is the one that is reflected from the bat, means the one when it is reflected it will have a different frequency than what was emitted. So that is why we had to calculate this one. So bat emitted 82.58, but when it strike the moth it was 82.8 kilohertz. Now approximately. Now this is the wave that is reflected. Now it has to go back and the bat will receive it as a receiver. Now this one becomes, now the moth becomes the source, because now it is coming from moth and going towards the bat, and bat becomes the detector. Now moth, just remember, moth is the source in now, and the bat is the detector. So this equation can be written for this. You just recall that when the detector is moving away from the source, this is the formula, because moth is still moving away, it is running away from the bat. So so here the bat, it was moving towards the source. Here this is the velocity of the bat, because now bat is the detector and moth is the source, because the wave is being reflected from the moth and coming to the bat. Bat is moving towards, that is why it is positive, and moth is moving away, or the source is moving away, that is why this one is positive. You can go back and see those formulas. Okay, when the source is moving towards and source is moving away from the detector, so you will realize that how to use these positive or negative signs. Now we put values and calculate the frequency. It is 83 kilohertz. This is the frequency that the bat will detect. Now notice that bat actually emitted 82.5 kilohertz, but when it reflected from the moth and reached the bat again, it was 83 kilohertz, right? It is more than what the bat emitted originally. Okay, so that's all for this lecture. If you have any questions, you come across some confusions or things which are not clear, you can ask me on Kaisala and I will respond to you. Thank you very much.